Sorry for the recording missing the first two. You'll have to ask your friends. A base in an exponential is what we keep multiplying by. So if I have a set of values here, 4/9 and 4/3 and 4 and 12 and 36, we can figure out that all of these are being multiplied by 3. And if they're all being multiplied by 3 to get my next answer, I know my base is 3. So we're going to start writing an equation. Here's an exponential form. G of x is going to equal, well, my base is 3 to the x. Now all I need to figure out is, what is my initial value? Well, remember, the initial value is the value when x is 0. What's the initial value of this one? 4. This is 4 times 3 to the x. I'd probably put parentheses there to make it clear. H of x over here, we are multiplying by 1/4. Now I know that's dividing by 4 each time, but we're curious as to what we're multiplying by. So if I'm multiplying by 1/4, I know my base is 1/4. What's my initial value on the h function? 8. When x is 0, I got 8. So it's 8 times 1/4 of the x. So that's just the understanding of what an exponential is. The base is what I keep multiplying by. Now, reviewing some things for any exponential function, here's the form that we have over here. To get my next term, when they say f of x plus 1, it just means the one more term from what I am currently on. If I was on f of x, then the next one is f of x plus 1, one more term. I just multiply the previous term by the base. That's kind of what we were saying. The base is what I just keep multiplying by. Now, when the bases are bigger than 1, that's where we get our exponential growth. So we know exponential growth. There they go. We've got a horizontal asymptote down here. And the base is called the growth factor because we're growing. And if the base is, now they say less than 1. A better way of saying that is between 0 and 1, because we're keeping our a positive. We're not getting negatives. So a base between 0 and 1. Those are exponential decay. We know what an exponential decay looks like, coming down like that. And then it's called the decay factor. The base is the decay factor. Keep on going down. So here is an analysis of one of these. Analyzing graphs, domain, all reals. We can put any x into our exponential function. The range, though, is from 0 to infinity, not including 0, going up to infinity. They are continuous. They keep going, no graphs. There's no symmetry to these. They're bounded below. We've got that horizontal asymptote on the x-axis, bounded below. There's no extrema to it. Horizontal axis, y equals 0, and this is the parent function. We can move them around, of course. There's no vertical. And if the base is greater than 1, then it is an increasing function. Always. It's always going up. And the limit of this function as I approach negative infinity, if I'm looking at the exponential growth, as I approach negative infinity, it's 0. And as I approach positive infinity, it goes to infinity. So that's the ending values of it. Now, if my base is between 0 and 1, we're decreasing functions. We're always going down. And here, the limit as I go to negative infinity is infinity. And the limit as my function goes to positive infinity is 0 because it's approaching the asymptote. So there's the analysis of them. So let's transform them. But we're used to transforming. We know how to stretch them and do stuff like that. So they say just take f of x equals 2x and sketch the graph by hand. Support it with a grapher. Well, I'll reveal it down here in a minute. So let's take this one. I have subtracted 1 onto the x. What does that do for it?
I just want to know if the asymptote will always be 0.
The asymptote is always 0 on the parent function, but we, of course, can translate it up and translate it down. Then it changes it. And we're talking about different transformations now. Subtracting 1 on the x. Do you remember what it does? Any function, right? Moves it right 1. We have just translated it, is the technical word, translated it right 1. So instead of being, and it's going to go through 0, 1, why will it go through that point? Well, if x Well, this one. If x is 0, what's 2 to the 0? 1. The parent things always go through that point. But if I've moved it right 1, well, now it's not going through 0, 1. It's going to be going through 1, 1. It's simply moved to the right 1. So it's going to look something like this. We will reveal our picture. Beautiful. The blue dashed was the original. This one just slid right 1. Now we have our first new transformation. We have never put a negative on the x before. We have put a negative in front of the equation before. What does that do if I put a negative in front of it? Reflects it over the x-axis. This one reflects it over the y-axis. That's all it does. Putting a negative in front of the x reflects it over the y. So let me do the blue dashed one. There would be the parent. I guess I should say what's happened. This is reflected across, over, wonder how you spell that, probably with an A, y-axis. So if I reflect this over the y-axis, it becomes this. Hey, what do we call one of those? Exponential
Decay.
Decay. Remember earlier we saw when there was a negative on that x? We went through what happened to it. That's all that it does. It reflects it across the y. There it is. So we get an exponential decay. And this is not new at all. What happens when I put that 3 right there in front? Which way? Vertically. It's going to be important. This is the vertical. We'll learn that soon. This is a vertical stretch by a factor of 3, so it's going to be 3 times as tall. So if it used to go through 0, 1, 2, 3, it's now going to go through 0, 3, because it's going to be 3 times as tall.
Is it what you're
Uh-huh.
Yeah. Thank you. I was like, what?
It's now going to be 3 times as tall. And it still is an exponential growth. Thank you. So, did we get it? You bet. We got it. There it is.
With decay. The middle one?
Oh, did I draw that one wrong too? That is awful. I did draw it wrong too. And then right down here, I even looked at it, and I never even picked up on that fact. The base is 2. It's bigger than 1. These are growth. Natural base E. We need to learn about this number. This is a number. We just use a symbol. Well, we know what that is. 3.14159265358. I don't know. All right. So pi is a number. That comes from taking the circumference of a circle, dividing it by the diameter. Did I do okay, Christian? Thank you. All right. Pi comes from a geometric relationship. E is also a number. It's an irrational number like pi. It doesn't come from a geometric relationship. It comes from an algebraic relationship, I guess we should say. Right here is one of the equations, and there's more than one way we can write how we get the number E. Notice it says you take the limit, which means I just keep going, making my x's approach infinity with this equation, 1 plus 1 over x, raised to the x. And if I make my x's bigger and bigger and bigger and bigger, I get the value of E to more and more and more decimal places. So when do I reach the end of E? Well, I don't, because I can just keep raising that x to a higher and higher power. So if you take, why don't on your calculators go 1 plus 1 over 999 raised to the 999th power, and tell me what answer do you get when you do that? Because 999 is pretty big. It's not infinity, obviously.
Yeah, I got 16,633 over 6120.
Give me a decimal.
2.71692.
All right, something like that. Now you also have this button, e to the x. Raise e to the first power.
So what's the difference between log base e, natural log, and...
We'll get to logarithms. But right now, e is just a number. This is a way of getting that number. 2.7182
2A.
2, 8, all right. See, that was where my 8, 2 came from. I was mixing it up with E, maybe, I don't know. So E is a number. The natural base is what it's called, and it's related to natural logarithms. That's why we call them natural logarithms, because they're dealing with the natural number, E. Now, E is a number that's almost 3, but it's bigger than 1. So if I did a function, f of x equals e to the x, it's going to be an exponential growth, because my base is bigger than 1. So this e to the x, it's exactly like any other exponential growth. All those answers are exactly like the ones we just reviewed a minute ago, because it's an exponential growth graph. It just happens to have e as the base to it. And e is a favorite number of mathematicians and scientists. It's just a beautiful number to use. You can write any exponential equation with base e. Any. Exponential growth, exponential decay, all of them. What do you think we need to do to make this an exponential decay instead of a growth like this? Yeah, negative x. That's all we have to do, and we've got a decay one out of it. So, see, we're learning this theory now. So right up here, they say, any exponential function in this form can be rewritten in this form. A is still the initial value. Notice they threw a little k up there. If k, a constant, is bigger than 0, then there's our exponential growth. If it is less than 0, if it's negative, that's where we get the exponential decay. Simple. So let's transform one of these things. Well, we know how to transform stuff. I mean, this is like kindergarten to us now. So let's see. E to the 2x. Whoa, wait a minute. We have not seen a multiplying the x by something before. Now, we have seen a 2 in front. Tell me what that did if I put a 2 in front. Stretches it vertically by a factor of 2. So if I put a 2 onto the x, it's a horizontal shrink by a factor of 2. Now, here's how I remember. Anything on the x's, the x-axis is the horizontal axis. Anything on the x's is dealing with a left and right change. So, remember if I subtracted 1 on the x, I moved right 1, it seems to be the opposite. Same deal's happening. If I multiply the x by 2, it's really half as wide, 2 times as small, whichever way you want to look at it. So this is a horizontal shrink by a factor of 2, or I'm going to say it's 1/2 as wide as it used to be. Yes?
So if it was one half exponential of x, if it was 1/2, it'd stretch it to?
It'd be twice as wide if it was 1/2 x. Yeah. So once you learn it, it's easy. So, all right, horizontal shrink. So this thing is not going to be quite as gentle because it's been squished together horizontally. There you go. See, it's been squished together horizontally. It's half as wide as it used to be. Oh, we know this, negative x. What's that one? That's reflected across the y-axis. There's my abbreviation. So, reflected across the y-axis. And it makes it a decay. The negative up there. Oh, this is easy stuff. This one?
Stretch 3.
And vertically stretched by a factor of 3. So this is going to be 3 times as tall again. Instead of going through that 0, 1, now 2, 3. And I'll see if I can make sure I make it an exponential growth this time. Say, too easy for us pre-calculus scholars. Logistic growth. Here's a new kind. Exponentials are very, very useful to a point. If I talk about, let's talk about a petri dish where you've wiped a little swab inside your mouth and then you spread it on this, what do they call that, agar, something like that, growth stuff. And then you close it up and you set it in the cabinet and shut the door and you come back a week later and there's all this bacteria on there. That grows exponentially. That's an exponential growth. Populations of people, of mice, take your pick. Populations tend to grow exponentially. But they can't do it forever. Let's go back to my Petri dish. Why can't the amount of bacteria in there infinitely grow exponentially?
Because the area of the Petri dish would be full.
Runs out of resources, whether it's the area of the dish, whether it's oxygen, whether it's food, whether it's a good economic thing. We run out of resources. So instead of going forever exponentially, there are many things that are very exponential in nature, but then they begin to level off at some maximum value. So wouldn't it be useful if we had an equation that made a graph like that? Well, yes, you say, it would be useful. They're called logistics functions. And you will need to learn the logistics function equation. Now, here's one way of writing it. Notice right down there, have you ever seen anything that looks like that? A times b to the x? Hey, that's just like a little exponential hidden in there. Here is another way of writing it. Ever seen anything that looks like that right down there? Yeah, you've seen that. Now, we can have logistics growth functions, which has happened to be what I drew right up here, and also what is down here in this graph. A logistics growth function, the b value is between 0 and 1. It's the opposite of what an exponential growth is. It's just like an exponential decay. If this little thing looks like an exponential decay, it's a logistics growth. And the same thing down here. See that negative? That is a logistics growth function. On the exponential, it would be a decay. But on this one, it's a growth. And again, we can write them either way. We really like the E over there, but we write them the other way as well. And the top value, the C value up here, this is called the limit to growth, or sometimes it is called the carrying capacity. My Petri dish, my bacteria, how much bacteria can it carry or support? Well, there's a capacity to that. It's called the carrying capacity. And so that C is going to be a horizontal asymptote, y equals C. And the parent has a y equals 0 horizontal asymptote on the bottom. Oh, so these aren't so bad. They already talked about growth. Oh, decay one. All we need to do is the b bigger than 1, and it becomes a logistics decay, or a negative k value on that e, and it becomes a logistics decay. Let's analyze. Well, domain, all reals. We can have all x's. Left to the right goes forever. All x's. Range, the parent is between 0 and 1. Notice the carrying capacity. I always call it that. What do they call it? Limit to growth. Limit to growth is 1. That's the top value on this one. So it goes between 0 and 1. They're two horizontal asymptotes. My range. Continuous, it's continuous. Increasing, always increasing this one. Symmetry, this one has symmetry right about the point that's right there in the middle. Between 0 and 1, 1/2. It has symmetry, it has point symmetry. It's bounded. Above and below, we've got these asymptotes. There are no extrema to this. There's our asymptotes that we keep running across. They're the ones that are bounding it. And what is the end behavior? Well, as I go to negative infinity, it approaches 0. As I go to positive infinity, it approaches 1. The carrying capacity, the limit to growth. Graph these functions. Find the y-intercept and the horizontal asymptote. That ain't no problem. As I look at this, I notice I have a 0.7b there. Is this a growth or decay? A logistics growth or decay?
Growth.
It's a logistics growth. And I have a upper limit of 8. I have right up here a horizontal asymptote at y equals 8. And I also have an asymptote right here at y equals 0. So this one goes between 0 and 8. Now, is it exactly at 4 in the middle? Well, let's find out. What is it when x equals 0? I'm finding f of 0. Well, if I put a 0 there, 0.7 to the 0 is 1. 3 times 1 is 3. 1 plus 3 is 4. What's 8 divided by 4? 2. This one happens to have a y-asymptote, a y-intercept at 0, 2. So the graph probably looks something like this. That should not come up over there. Probably looks something like that. My curve is slid to the right a little bit here, and this one is not right exactly in the middle. So
we wouldn't consider this one symmetric, right? Not symmetric.
well, it does have symmetry, but it's down here somewhere. Don't know where it is, but it's down here somewhere. I mean, there's a way to find it, but we haven't done it. It's down here somewhere. All right, this one. Well, there's my 20. So there's my top. Y equals 20. And I've got my y equals 0. And now my k is negative. What does that mean? Because this is a basic. It's growth as well. It's growth. And let's go ahead and find the y-intercept, which is f of 0. Well, that'd be e to the 0, which is 1. 2 times 1 is 2. 1 plus 2 is 3. 20 divided by 3. Giving that as a mixed number. Or a decimal, I guess. 6 2/3, right? 6 2/3. So if that's 10 halfway through, there's 6 2/3. Here's another one that is kind of slid off to the right somewhere, looking like this. Let's go to our calculators. Let's see if we can enter one of these things. So I can bring my calculator into here, and I probably didn't give myself enough. There we go, I can reach my buttons. Y equals, clear out any other junk, turn off any plots if you have any plots. 20 divided by, and use parentheses for everything down there in the denominator. Your E button is right above the natural log. Make sure you use the negative button, not the minus. I'm going to zoom standard. That's not going to quite do it for me. I'm not going to zoom standard. Let's hit window once you get that thing entered. My X's, I think, are okay, negative 10 to 10. But my Y's, I'm going to go from negative 5 up to 25 because I know 20 is that top.
Why do you put your y minimum below 0?
I like to see my x-axis. Look at that. There it goes. Now I could shrink up my x scale a little bit. I'm going to change it to negative 5 to 5. That way I can see the details a little bit better. Otherwise it was so squashed together that I could hardly see the curve as it came through. All right. This logistics growth might turn into something handy for us at some point. Oh, there it goes. There's the second one. Mine was not near as steep as it should have been on my curve. Modeling Jose's population, San Jose's population, assuming the growth is exponential. Now that can't go on forever, but it can for a while. When will the population of San Jose surpass 1 million persons? Exponentials look like this. But if we're talking about populations, we often use different variables. Population at time t equals the population at time 0 times a base raised to t, the time that goes by. Exactly the same formula, exactly the same equation, just different variables. Well, if we look over here, I have a 1990 population of this amount. So let me just fill in this equation. I have 782,248 people. I don't know what the original population of San Jose was. I don't know when it started. Some base. Oh, just a minute. I did that one wrong. In the year 2000, 10 years after 1990, I have this population. So let me start that again. 895,193 must equal, I don't know the population at time 0, I don't know my base, but I do know 10 years have gone by. What am I trying to do here? My population at time 0, I'll get this right eventually. My population that I start with is 782,248. There, I finally got it warmed up. This 895,000 will equal my starting point 10 years later. So I need to try to solve for the b in this. Well, I need to get rid of this 782,000, so I need to divide by that number. What do you get when you divide by that number, if you would do that on your calculators? And just leave it in there. 1.14385, da-da-da-da. Just leave it in there. Now, if b to the 10th equaled that, how would you find b? I need to take the 10th root, which also can be raising it to the 1/10th exponent. I need to take the 10th root of that that answer you had in the calculator. 144, da, 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 da. What do you get for b? And why don't you tell me, about 3 decimal places. Let's not round it off too much.
1.013, well, like the 1.014.
1.4 if we rounded it there. So now I have an equation. The population at any point in time, if we continue exponentially, should be 782,248 times 1.014 raised to the t power. If I go exponentially, this is the rate that San Jose is going on. Now they wanted to know, when are we going to hit 1 million people? Instead of saying equal to 1 million, let's go to our calculators and see if we can't let our calculators help us out on this one. So let's graph this equation. 8, 2, 4, 8. Thank you. Somehow I missed. I can insert. Not sure where it's going to put it. Didn't put it where I wanted it to put it. All right. Now I need to mess with my window a little bit here. So my x's, I'm going to start at year 0, which would be 1990 in this case. And we're going to need to go several years down the road. 10 years took us up to that 895. So maybe I'll go 30 years down the road, and hopefully that's good enough. My y minimum, 0 is okay. Now I'm supposed to get to 1 million. So I'm going to go to 1.2 million. 1,200,000. At my scale, I'll probably change it to 100,000. I'm going to hit graph.
Yeah, just go straight up.
Depends on what you chose for your window. Here was mine. Now what I needed to have done is I needed to have stuck in my second equation of, when do I reach 1 million? 2, 5, 6, 0, something 3, 4, 5, 6. And looks like I got it. So when do I reach 1 million? I'm going to calculate an intersection. First one, second one, and my guess is right there. I reach 1 million. 17.7 years later. Now we started in 1990, so when is it? It's about 18 years later. What year do we reach 1 million? 2007, 8, somewhere in there. 2007, 2008 is where we happen to reach 1 million population. So there we go. There's an intersection of it. Oh, what do I got at 18.18? I bet I didn't round it off the last time I did it.
Okay, wait, did you get 17.6 on yours?
I got 17.7 on mine. It'll depend on how far out you take that base.
Okay.
Is what happens. Well, let's try Dallas's population. Some of you maybe are familiar with that. Now, this is real data. Based on a recent census data, a logistics model for the population of Dallas 2 years after 1900 happens to be this. Now, I want you to tell me what is the limit to growth of Dallas's population according to this? 1.3 million. Okay? According to this model, when was the population a million? Go ahead and start entering it in. See if you can do it. Do a y equals a million. I'll start entering it in. Let's see if you can't. No, you don't have to beat.
Nah, I'm just kidding.
That's what you want. 'll leave my window the same as I had before. Something's not looking very good.
Is that 21.602?
21.602. Anybody have a graph that looked better than mine did when you... You should be getting a graph that's looking like that. I'll have to go back and see what I did wrong here in a minute.
It's just turn your axis around the...
My X was not good enough?
I could find the X max 100 and it was pretty low.
X max of 100. Let's try that. No, I've entered something wrong. I've entered something wrong on this one. I'll go back and enter it and see what I did wrong, but we won't take more time on my mistake. Here is the graph of what it's supposed to look like. When will it reach a million? Well, there's an intersection there. Notice the blue is a nice logistics growth. 84.5 is what you should be getting. So if this is T years after 1900, they're saying in the year, 1984, 1985, we should be at a million. Now I want to use this same equation. And does anybody, well, Lily has it right at least. I don't know if any of you, all right, some of you have it doing well. Go back and let's do a trace for the year. Did I look up the year? Oh, 2010. That's the last census. 2010. How many years since 1900 is the year 2010? 1900 to 2010. How many years later? 110. Stick 110 into your X, and what's the answer that you get?
Why?
1.2 million?
Yeah, that's not right.
Anybody else? I mean, I'm
I got
just...
1.2.
Okay, 1.2 million. Here was the actual population. Ooh, that's close. That's 1.2 million. That's really good. So this is real data that we're working with here on that one.
It's supposed to plateau soon.
And about 1.3, yeah, is what they're saying. I'll look up here and see if I have another census number, and we'll see. Now remember, this is just Dallas, the Dallas proper. It's not the whole metroplex.